Welcome to the deep dive. Today, we're tackling something called the CAP theorem. Sounds a bit technical, maybe.
It is, but it's super important for understanding how lots of online systems work, especially systems that spread data out.
Right, distributed systems. So we've looked at some sources, and our mission for this deep dive is pretty clear. Get a handle on CAP, what it is, why it matters.
Exactly. It's all about three key things a distributed database tries to do, and, well, the hard choices involved.
Okay, let's jump in. The CAP theorem, what's the core idea? Lay it out for us.
So basically, Brewer's CAP theorem says you have three desirable properties: consistency, availability, and partition tolerance.
C, A, and P. Got it.
And the theorem states that any distributed system can only strongly guarantee two of those three at the same time.
Only two. Okay, interesting. So there's always a trade-off.
Always. That's the fundamental constraint.
All right, let's break them down. C, consistency. What does that actually mean in this context?
Consistency means that whenever you read data from the system, from any part of it, you always get the absolute latest, most up-to-date version.
Like everyone sees the exact same thing at the exact same moment.
Pretty much, yeah. Think of it like a single source of truth, instantly updated everywhere.
Okay, makes sense. Now, A, availability. What's that promise?
Availability is simpler, kind of. It just means that every request you send to a working part of the system gets a response.
It doesn't just hang or give you an error, assuming the node you're talking to is okay.
Exactly. It's available, it answers you, usually within a decent time frame. It won't just ignore you.
Right. And the last one, P, partition tolerance. This sounds like it's about things breaking.
It is.
Yeah. Yeah.
Networks aren't perfect, right? Sometimes the connections between different parts of the distributed system, they can fail or get really slow. That's a partition.
Like a temporary split in the network.
Yeah. Partition tolerance means the system keeps operating, keeps doing something useful, even when those network splits happen. It doesn't just fall over completely because parts can't talk to each other.
So, consistency, availability, partition tolerance. Why the conflict? Why can't we just have all three? Seems like we'd want them all.
You would. But think about what happens when a partition does occur. Imagine the system is split into two sides, A and B, and they can't talk.
Okay.
Now someone sends new data, a write request, to side A. What does side A do?
Well, it has the new data.
Right. But side B doesn't know about it because of the partition. So if side A accepts the write, and someone then asks side B for the data,
They'll get the old version. The system isn't consistent anymore.
Exactly. So to maintain consistency, side A might have to refuse the write, or maybe stop answering requests altogether until the partition heals.
But if it refuses requests, it's sacrificing availability.
Precisely the dilemma. During a partition, you're forced to choose. Do you prioritize keeping the data perfectly consistent everywhere, sacrificing availability? Or do you prioritize keeping every working part responsive, potentially sacrificing immediate consistency?
Ah, okay. That clarifies the trade-off. So real-world systems have to pick a side, more or less.
They do, based on their needs. Think about, say, your bank account.
Right. Definitely want that to be consistent.
Absolutely. You can't have one ATM showing a different balance than your online app. So banking systems typically favor consistency, often labeled CP systems. They might become briefly unavailable during certain failures to ensure the balance is never wrong. They use complex methods, like consensus protocols for this.
Okay, CP for consistency and partition tolerance. What about the other way around? Prioritizing availability, an AP system.
Think about maybe a social media feed or like counts on a video.
Yeah, you want that to load fast. Always be there.
Exactly. It's more important that the service is up and responsive, that you can see posts, even if maybe like count is slightly delayed, or posts appear slightly out of perfect order for a moment across different servers.
That's called eventual consistency, right? It'll catch up eventually.
Right. They prioritize availability and partition tolerance, AP. The system stays up, keeps serving requests, even if it means data isn't perfectly synchronized immediately across all nodes. It settles down over time.
So these network partitions, they're not just some theoretical rare thing then.
No, definitely not.
Yeah.
In large-scale systems, especially cloud environments with hundreds or thousands of machines, network glitches, delays, temporary partitions, they happen. It's a fact of life.
So the CAP theorem isn't just academic, it's practical engineering.
Totally. It forces engineers to think up front, okay, network partitions will happen. When they do, what do we care about more? Perfect consistency right now or staying available right now? Designing for that choice is key.
And this directly impacts cloud services, all the stuff running on AWS, Google Cloud, Azure.
Absolutely fundamental. Cloud architectures are inherently distributed. Databases, storage systems, message queues in the cloud. Their designers made explicit CAP trade-offs. Understanding CAP helps you understand why certain cloud services behave the way they do, especially under stress. It guides architectural choices.
Wow. Okay. So summing it up, distributed systems face this unavoidable choice imposed by the CAP theorem. You've got consistency, availability, partition tolerance.
And in the real world, especially when the network gets unreliable, you can really only guarantee 2 out of 3. Usually the choice boils down to CVSA, because partition tolerance is something you generally have to deal with in distributed systems.
So CP or AP is often the practical decision.
That's a very common way to frame it, yes.
Okay, really interesting stuff. So a final thought for you listening, next time you're using an online service, maybe your banking app versus scrolling through social media, think about it. Which one feels like it must be perfectly consistent, even if it glitches occasionally?
And which one feels like it absolutely must be available, even if things are sometimes a tiny bit out of sync? It really puts the CAP theorem into perspective in your daily life.
A great way to think about it. Thanks for walking us through that.
My pleasure.